Hi everyone, so we're going to look at a second example of when the force that's acting to cause a moment is not acting perpendicular to the point about which we're taking moments. And just before we do that, we're going to look at a couple of similar but different situations with a rod that's either resting on the floor, on a wall, or it's hinged. And these are quite different situations, although they look very similar. And so we're looking in the question particularly for this word if something is hinged at a point. Okay. So if the rod, so this purple bit here, if the rod is resting at A and B, if it's just sort of sitting there, then what happens then? The reaction force at this bottom point is just sitting on the floor. So there's a reaction perpendicular to that foot of the ladder. Often these are called ladder problems, not always, but quite often they are. So there we'd have a reaction at A perpendicular to the floor, where this ladder is touching the floor, the weight of the ladder acting downwards on the floor. And we'd also have a reaction force here at B, where this ladder is leaning against the wall that way. So again, we have a reaction here, perpendicular to the wall at B. So if it's resting or touching or leaning just against the wall and against the floor, then we've got these reaction forces. Okay. If, however, it's hinged at A, then there's something else going on here, because that means this is now joined at A and it's movable. This is just sitting here. This is now movable. And what happens then at A? We have a reaction force that isn't just in one direction. Okay, we have this kind of perpendicular and parallel reaction forces, components of this reaction forces, so that overall at this hinge there's some other reaction force going off at some angle, and depending on what this is doing, that's going to change. And the way that we work questions like that is we look at the components of the reaction in the y direction and the component of the reaction in the x direction. Okay, but that only happens in questions where things are hinged, where this is fixed and it's a point like this. So there's some forces going on here at the hinge as this is moving or allowed to move, whereas this one is just resting against this. And we just need to bear that in mind in questions. So this again is a really important word to look out for. And if this happens, quite often we can take moments about A, so we don't need to worry about them, but in other questions we might be asked about this in particular. And in chapter 4, we're just going to look at quite a simple example of this. As we get on later on in the book to chapter 7, we'll do quite a lot more work around this sort of question. Okay, so let's look at our example. So we've got a uniform rod, PQ. It's hinged, so there's that word straight away. It's hinged at point P, so there's something going on here at P because this thing is hinged at that point. And it's held in equilibrium at an angle of 50 degrees. It's held in equilibrium by this force here. So we've got this rod and there's some force here. It might be a string or someone pushing it, pulling it this way, pushing this. It doesn't matter. We've got a force here that's holding this thing in equilibrium, because if that wasn't there, it would be hinged here and it would move. Okay. And that's perpendicular to the rod. Given that the rod is of length 3 metres and mass 8 kilograms, find the value of F. So that's our question here. The other thing that's important in the question is this idea of this thing being uniform. And what I've done, I'm going to do 2 different methods for this. And so I've got 2 diagrams here. So I've just drawn this out. It tells us it's uniform. So if this whole distance is 3 metres, then this must be 1.5. And so must this. So I'm just going to put them on my diagram. And then I think we've got all the information on our diagram. Okay, so let's have a look at this. It says it's hinged at point P. And this is my point P. So it's hinged here, okay? So if I'm going to be looking at the forces at that point there, at the reactions at that point there, because it's hinged, I've got a reaction force in the y direction and I've got a reaction force in the x direction. It's not just leaning on the floor, not just resting, it's hinged at this point. So that's what's happening there. So I'm just going to put that on both of my diagrams. Okay. So if I take moments about some other point, I'm going to have these reactions involved in that, these unknowns. So what I'm going to do here, I'm not interested in them in this particular question. It's not asking me about them. I'm just going to have a look at taking moments about this point here And then I don't need to worry about these. And if I did vertical and horizontal, I'd still have to worry about these as well. So I'm going to take moments about point P. So tell the examiner what we're doing. I'm going to take clockwise as positive. So let's have a look at what's happening. So this force F is tending to have an anti-clockwise moment. I'm just going to put that one on there because that's a bit easier to do. And the perpendicular distance of the line of action of that force to our point P is definitely 3 meters. Okay, this force now is tending to pull me clockwise. It's pulling down this way, so the moment is clockwise. So that's plus 8g. And in this question, the way I'm going to do this, I'm going to look at the perpendicular distance here and try and find that. So if we look at this, I've got this force acting downwards here. So the perpendicular distance from the line of action of that force and this point is this distance here at the bottom. So let me just do sort of that. So this is the distance that I want here. And this distance, if we look in this right angle triangle from some of the work that we did in that last example as well, this distance is going to be adjacent to this angle, so 1.5 cos 50. Okay, and it tells us it's an equilibrium, so that must be equal to 0. There's nothing actually turning here, so the sum of the moments must be 0. Okay, so let's sort this out. So rearranging, 3F is going to be 8 times 9.8 times 1.5 cos 50. So 75.5918. Divide that by 3. So F is 25.1972. So 25.2 newtons to 3SF. Okay, so that's method 1. So I'm just going to pull this sheet of paper across a bit to get this working in the middle. Now what I'm going to do for method 2, so this was finding the components of the distance. In this one, I'm going to find components of this force parallel and perpendicular to the rod, and then hopefully I'll get the same answer as this. So let's have a look at this 8G. So if I think about it, if this is 50, thinking about this triangle that we drew here, this angle would be 40, so this angle would be 40. And so what I'm going to do, I'm going to put these components on. And if this is 40 degrees, then this one is now the one that's cozy with this, it's adjacent. So this component is going to be 8G cos 40. And this component then is going to be 8G sine 40. Okay, so that's what I've done. I've split this 8G into its components. So instead of looking at the action of 8G, I can look at the action of these two components, which is equivalent to this. Okay, let's do the same thing then. Let's take moments about P. Positive as clockwise. Clockwise is positive even. And then about here, well, minus F times 3 again, anti-clockwise. This force now, the 8G cos 40, this one, the line of action of this, is directly through my point P. So in this force, in this one, this component, 8G cos 40, the line of action is through P, so that doesn't have any moment at all because the distance is 0. So the only one that's having any effect is this component, pulling us clockwise. So 8G sine 40, and that's going to be 0. And if we look at these, sorry, I need to times that by the distance, don't I? So my distance there is 1.5. My perpendicular distance of this component from this point is 1.5 meters there. Okay, and if I look at this, this is really similar to this. The only difference here is the sine 40 and cos 50. But sine 40 and cos 50 are exactly the same because cos of 90 minus theta is the same as sine theta. So these are definitely going to give us the same answers, but let's just check that on our calculator. So 8 times g times 9.8 times sine 40, and then my 1.5 is my distance, and then Let's just check that. I can see I've made a mistake there, look, 0.98, so let's go back in and sort that out. So 9.8 for G, so there we go, 75.5918, same as here, so F is equal to that divided by 3, so F is equal to 25.2 newtons to 3SF. That's definitely right because it's the same answer. And clearly in this one, this looked a bit simpler doing this by the perpendicular distance rather than looking at the components of the force. But in some questions, and particularly later on in this mechanics module, we are going to have to start splitting our forces up, and that's another topic that we'll look at. So that's that second example finished, and that actually is that chapter finished. So I'll set you some questions to do on this as practice.